The OVRCOAT model mitigates objectness bias and reduces region-to-text misalignment in open vocabulary panoptic segmentation. Closed vocabularies do not survive the real world. Therefore, recent panoptic segmentation methods have moved on from the closed vocabulary setting into an open vocabulary one, hoping to generalize from the closed vocabulary labels to new novel labels that are seen only during inference. To do this, they rely on foundational models in the following recipe. First, they generate mask proposals, then they reject low objectness masks, and finally they classify the rest using a VLM, for example, CRIP. Recent models have two bottlenecks. The first is mask selection bias. In the example to the right, we can see FCCrypt and MAFT plus the recent state of the art both struggling to segment paintings in the background. The reason for this is that both models are trained on the COCO dataset. In that dataset, paintings are present in the images. However, they are not part of the labels. Therefore, the model could learn to segment them. However, those masks would be discarded as background, resulting in a bias that continues during inference. The second issue is region-to-text misalignment. Visual language models such as Script are trained on image-to-text pairs. The label embeddings are not aligned with regions, reducing performance in segmentation tasks. We propose OVRCOAT. OVRCOAT is made up of two components. The first component is OVR. This is our training approach for the clip image encoder. The second is COAT, which is an inference component which mitigates the objectness bias we discussed. First, we take an image and give it to the clip image encoder that has been tuned with OVR to give features that are more aligned for the segmentation task. Then we pass those features to a mask transformer, which is a closed vocabulary model that outputs masks, an objectness score, and the per class probabilities generated by that model. In our case, this is mask to former. Then we take the masks, we do mask pooling on the image features generated by clip, and get segment embeddings, which we compare with the text embeddings of our labels. This gives the per class probabilities of the clip model. The clip and mask transformer per class classification probabilities are geometrically ensembled into the final classifications. Then COAT updates the objectness score using the clip certainty, which is the maximum clip assigned per class probability for the respective mask. Finally, the per class probabilities and the masks are combined into a panoptic segmentation. The COAT module relies on CLIP as a foundational model, leveraging its large pre-training dataset, believing that if CLIP sees something in a segment, there is likely something there. We update the objectness score using the formula on the bottom left. The idea is if the mask transformer gives a low objectness score, but CLIP has high certainty, then this would reduce the probability of there being nothing in the image, and that would increase the final objectness score. The second component is OVR, which we use to refine CLIP for region-level alignment. This is a two-stage training pipeline. The diagram on the left follows essentially the inference diagram we showed earlier. In the first stage, the OVR clip image encoder is frozen. Then we train only mask transformer using the mask to former loss as a closed vocabulary model until it plateaus. In the second part, we unfreeze the clip image encoder, tuning the produced clip probabilities using a binary cross-entropy loss, and combining said loss with the mask to former loss, giving the final loss for the model. The result is a stronger region-level alignment and improved classification. OVRCOAT sets a new state-of-the-art on 3 out of vocabulary benchmarks, achieving from 3 to 7% relative panoptic quality improvement. Qualitatively, we can see OVRCOAT's performance in the following examples. It does better in segmenting smaller and finer objects, as we can see in the first and third scenario with the bows and the bottles. In the second scenario, it manages to recover the toys, and in the last scenario, we can see that it recovers doors and segments the pillars, unlike FCClip. Not only does OVRCOAT have a higher panoptic quality compared to the previous state-of-the-art MAFT+, but it also uses 56% less memory during training. On the component ablation to the right, we can see that both the COAT and OVR module contribute to the OVRCOAT performance. On the bottom right, we can see a comparison of seen and unseen classes on 8020K, with the unseen classes having a noticeable improvement and the painting class, which was problematic, increasing by 192% relative panoptic quality. The key takeaways are simple beats complex. OVRCOAT offers a simplified architecture which surpasses far more involved recent approaches. Due to this simplicity, it is a better foundation as it is easier to extend. Finally, it is practical as it uses 56% less memory compared to MAFT+, the recent state of the art. Thank you for your attention.